Hi everyone, welcome to the last video from the series on hypothesis testing. Don't expect any heavy mathematics anymore and relax. The video will be more like a bunch of closing remarks. In particle physics, you will certainly hear people talking about the look elsewhere effect. Its essence is that it is easy to find a high discrepancy between data and an established theory, like the standard model, if we look at many parts of the phase space bins. For example, if we look at 1000 bins of the diphoton mass spectrum, then we should find one bin with a 3 sigma discrepancy. Unfortunately, this is a typical situation when searching for bumps at an unknown mass, and it's just because data drawn from the background-only hypothesis fluctuate. Such a high discrepancy in a bin is called a local p-value. We should avoid claiming a discovery based on the local p-value if the look elsewhere effect is important for our analysis. We should rather reduce the high local significance to a significance of the whole histogram. Such a global significance is called a global p-value. Let's take just one of many examples how this reduction can be done. The example is the bump hunter algorithm that is used by Atlas searches for digit mass resonances. Moreover, we simplify the algorithm here because we are interested in just the transition from the local to the global p-value. So, we are looking at the digit mass Atlas spectrum, and the spectrum has many bins. In a first step, we look at each bin individually, and we perform a test of the background-only hypothesis, just with the use of the one bin. This first step results in a set of local p-values, one p-value for each bin. Most of them are pretty high, as expected, but some of them can be low. This is also expected. Then, in a second step, we do a hypertest, as the bump hunter algorithm calls a test based on the whole histogram. The test statistic used in the hypertest is the lowest p-value from the one-bin tests. Of course, the distribution of this test statistic has to be determined with pseudo-experiments. Then, the global p-value is given by the integral from the observed value of the test statistic down to 0. In the bump hunter case, it was possible to account for the look elsewhere effect in a rigorous way. However, more generally, we may wonder about how likely it is that a search in a particle physics experiment observes a high discrepancy between data and the standard model. There are hundreds of new searches each year. Shall all searches be considered when observing an excess somewhere? Obviously, it wouldn't be possible, but in some sense, it would be the correct way. In the end, these thoughts just bring us to one conclusion. The treatment of the look elsewhere effect is quite subjective. A question partly related to the look elsewhere effect is why particle physics requires such an extremely high significance to claim a discovery of a new phenomenon. Obviously, one of the reasons is that the look elsewhere effect is impossible to take into account fully, to say. However, there are more reasons. A very clear one is that the discovery of something new in particle physics is groundbreaking, and therefore we require a high confidence in the result. Another important reason is that we are unsure about our description of systematic effects. Despite the enormous effort particle physicists invest to their determination, systematic effects are very tricky to evaluate and describe. Last but not least, people are unsure about their knowledge of the extreme tail of the test statistic distribution. The Wilks asymptotic formulae might not be perfect in this tail. Or, when generating pseudo-experiments, there is just a very tiny fraction of the total statistics in the tail. So, that's it basically. Particle physics requires 5 sigma to claim an observation, and who doesn't like it, he or she can do medicine, for example. The required significance is much lower there. Let's say that there is an intermediate step in particle physics between nothing and an observation. It is called evidence, and it requires just 3 sigma significance. The evidence is used when searching for a phenomenon that people strongly expect to exist, but that is very difficult to observe. So, we are done with hypothesis tests. We hope to see some evidence that you like the course, and at the end, we are looking forward to observing the best grades.